Hi friends, in the second part of the video, we have completed the number representations starting with the sign magnitude 1's complement and 2's complement representation. We have seen the merits and demerits of all the three schemes, but we have seen that 2's complement representation is most popular or widely used because of two major reasons. One, representation of plus 0 and minus 0 is unique, and second, for arithmetic operations, 2's complement method is better as we can neglect carry during such arithmetic operations. So now let us pass on to the next concept, big endian and little endian. In computers, you might have heard of big endian and little endian. This is referred to how data is stored in a memory. For example, if it is a 32-bit data, 32-bit means, as we know, memory comprises in 8 bits or bytes. So to store 32 bit of information in a memory, we need 4 consequent locations in consequent order, sequential order. So if the system is big endian, the information stored in such a way that the most significant byte is stored from the last memory address, whereas with the little endian architecture, the least significant byte will be stored in the lowest memory address. For example, let us consider that memory address be of 16 bits, say starting with the 2000. So memory address 2000 means it's in hex, each digit represents 4 bits. So 2000 shows a 16-bit address location. So 2001 location, 2001 second location, 2003 third location, and 2004 fifth location, and so on. So 2000 is the lowest memory address, followed by 2001, 2002, and 2003. So in the case of big endian scheme, the most significant byte will be stored in 2000. That's followed by that in 2001, the next one in 2002, and the last or the least significant byte will be in 2003. This is just the reverse with the little endian architecture, where the least significant byte will be stored in 2000, the lowest memory address. This is followed by 2001, 2002, and 2003 has the highest or the most significant byte. So that's the difference between the two endian schemes. So endian refers to the order of storing bytes in a computer memory. This is very important concept. There's an example is shown here. If it's a 32-bit integer, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2 being the most significant byte, 78 being the lowest significant byte. So depending on the type of big endian or little endian, the highest byte, that is 12, will be stored either in the lowest or highest memory location. That depends on the type of or rare type of endian architecture. So that is about endian. Now let us see floating point representation. So already we have seen integer representation, we have seen sign number representation. Now we go for a floating point representation. A floating point representation is used to represent very large numbers, say 1.23 into 10 to the power 88, or very small number 1.23 into 10 to the power minus 28, or very large negative number minus 1.23 into 10 to the power 88, and very small negative number minus 1.23 into. So that means that a floating point representation can be used to store data or numbers of any lower value to any higher value, that which is not possible with the conventional integer or signed number representation. Generally, the floating point representation takes the form f into r raised to e, where f stands for the mantissa or the fractional part, r stands for the radix, and e stands for the exponent. F is mantissa or fractional part, r is the radix, and e is the exponent. So the fractional part, radix part, followed by exponent. This is how floating point numbers are represented. So if it is a binary number representation, so r takes the value 2. If it is decimal number notation, r takes the value 10, and so on. For example, 55, suppose you consider a decimal number 55.66. This can be represented as 5.566 into 10 to the power 1, or can also be represented as 55.66 into 10 to the power 0, or can be 0.5566 into 10 to the power 2, or can be 0.05566 into 10 to the power 3, or can be 556.6 into 556.6 into 10 to the power minus 1. That shows that the representation of floating point representation is not unique. Now, The major limitation with the floating point number is it suffers from loss of precision when represented with a fixed number of bits, because we know that being a very large number or being a very small number, it's not possible that you can represent floating point numbers in a fixed number of bits. And it's going to be less efficient than integer arithmetic because of, or otherwise we need a dedicated floating point coprocessor. In some of the process, in earlier processors, we were having coprocessor for processing floating point numbers due to this reason. And for a floating point number representation, as we have seen there, we have three components are there. First one is a sign bit. The second one is exponent, is called usually generally represented by using bias notation. And third one is the fractional part or the mandisa. So for representing floating point numbers in computer, we have two schemes or methods are there. One is IEEE 754 32-bit single precision arithmetic representation, and second one is IEEE 754, that's the standard format, 64-bit double precision representation. So two ways we can represent floating point numbers in computers. If it can be represented in 32-bit scheme, can also be represented in 64-bit scheme. If it is 32-bit scheme, we have a sign bit followed by exponent part and then the fractional part. Sign bit for one bit is for sign bit, 8 bits for exponent, and 23 bits for fractional part. Total 32 bits. So sign bit will be 0 for positive numbers and 1 for negative numbers. Exponent is 8 bits. Generally we use biased exponent with bias as 127 for 8-bit representation and 1023 for 64-bit representation. The exponent length of exponent part in computer representation for 32-bit representation is 8 bits, whereas for 64 representation, instead of 8-bit, it is going to be 11 bits. And the last part, excluding the most significant bit, it will be 23 bits that represent the fractional part or the mandisa part, and that corresponding value in 64-bit representation is 52 bits. So total, first case we have 1 plus 8 plus 23, 32 bits, and second case we have 1 plus 11 plus 52, 64. This is how floating point numbers are represented in computers. And I'll give an example also. For example, suppose I have a number, say 1.01 into 2 to the power 5. Suppose this is a number. So this is positive number. So if I am going to represent by using 32-bit representation, then it will be sign bit is 0, sign bit is 0. This is followed by exponent. Exponent to be represented in 8 bits. So if we have 5, I'm not now using sign representation. So 5 using 8 bits, 0, 0, 0, 0, 0, 1, 0, 1. So this 8 bits represent the exponent part for 5. And this 0 represents the sign bit which is plus 0. Please do remember, even if I have written here as 8 bits, 5 for exponent part, in bias, generally one bias notation is used. With the bias notation, we will be adding 127 to 5. So it will be 132 instead of representing this 5 in binary form. We'll be using 132. The representation of 132 in binary will be representing 8 bits. So that is a standard concept. And this is followed by the mandisa part. And the leading one will be excluded for representation. So we have 0, 1 followed by how many zeros? 23 zeros. Why 23? Because total 32 bits. So this is 1 bit. This is how it is represented in 32 bit. If it is 64 bits, again there must be 0, 1 bit followed by, in 11 bits we have to represent the exponent. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 bits we use for representing exponent, that is 5 here. This is followed by 52 bits for the mandisa part, 0, 1 followed by how many zeros? 50 zeros. So this is how numbers are represented by using floating point. So with this, I'm concluding the representation of numbers in computers. So as a summary, we can see that we have seen integer representation, which is used to represent zeros and positive numbers. That is followed by sign numbers for representing zeros, positive numbers as well as negative numbers, wherein we have seen that 2's complement notation is widely used to represent negative numbers in computers. Then we have seen big endian and little endian. we have seen what is the difference between big Indian and little Indian. That is nothing but how a number of bits or byte in a data is stored into the memory locations. So do remember that all memory locations are of 8 bits in length or single byte. So if you have to represent 16 bits, means 2 bytes, 2 memory locations are required. If you have to represent 16 bits, sorry, 32 bits, 4 memory locations are required, and so on, so on, so on. So depending on the type of Indian storage, the least significant byte may occupy lowest memory locations, or highest byte may occupy lowest memory location. That is decided by little Indian or big Indian nature. Then we have seen floating point numbers representation. Why floating point numbers? To represent very small numbers as well as very large numbers. No other option we have to represent very large numbers. Please do remember, while floating point numbers are converted to integer part, there is a chance of having less precision, but still we have to use it. So in computers, in earlier microprocessors and microcontrollers, use floating point coprocessor for making the floating point operation fast. That is why the speed of conventional processes are expressed in terms of megaflops or teraflops, floating point operations per second. The floating point operations is going to govern the speed of architecture. With this, let me conclude third part of video, and the next part of the video will be on the basic architecture of microcontrollers. Thank you.